Okay, so let's look at this example. So we're asked to show thermodynamically that the internal pressure, which is given, which is pi T, is equals to 0 for a perfect gas, and then we also need to compute this for a van der Waals gas and interpret this, the latter results, in other words, what it is for a van der Waals gas. So let's first just write down what the definition is for the internal pressure of of a gas. So in other words, this would be pi T equals to du dV over T. Right, so that is our principal definition. And what we say show thermodynamically means we want to find an expression for this pi T only in terms of temperature, pressure, volume, moles. In other words, something in terms of, so pi T as a function of pressure, temperature, volume, moles, right, is equals to something. And of course they say we can use equations of state, whatever, by implication. So an equation of state, of course, is like the perfect gas. It is, we have PV is equal to nRT. So there's only constants and measurable quantities in there because all these quantities are measurable. So PV is measurable, N is measurable, T is measurable, and R is a constant. So in other words, an equation of state is something that consists of measurable quantities. Right, and similarly, we want something for this internal pressure of a gas to have a measurable quantity, or to be expressed in measurable quantities. So in other words, at the moment we don't have something, we just have a derivative. So we would need to have some sort of a plot of the internal energy variation, or the isothermal variation of the internal energy with volume. And we would have to take the derivative of that graph. That's essentially what this is telling us. So we would need basically something that is U versus V, and it does something like that, and then we would take the derivative of this line. So the slope of this line would be equal to pi T, right? So that's what we need to do at the moment, but we want to find some way of actually calculating that directly from pressure, temperature, volume, number of moles for certain gases. Okay, so that's what the problem, or the what we actually want to try and do in this example. Okay, so where I want to start is actually with, so our only problem really here in the expression for the internal pressure is that internal energy. So what is internal energy? Well, we can start with our fundamental equation, which says that internal energy is equal to TdS minus PdV. Okay. And then we need to find some clever way to make the internal pressure pop out of that, and then also to get rid of any unmeasurable quantities. So immediately, I mean, if we divide everything by dV, so in other words, if we say we divide by dV, we divide by dV, and we divide this term also by dV, then we would be left with, so at constant temperature, we can say constant temperature because remember this temperature is constant here, so it is isothermal. Then we can make this more general by taking the partial derivatives of it, saying that that is that, giving a bit more information. Then we're left with temperature is constant, so in other words it goes outside the derivative. We're left with ds over dv, of course at what? At constant temperature, minus p, and then dv over dv is just 1, right? So we're not going to worry about that. I know all the mathematicians are, of course, appealing right now, and they're burning tires in the streets because we've just done what's it, infinitesimal cancellations. Technically not what I've done here. What I've done is I've done the whole 3.5 page derivation to just prove that dv over dv is 1. Okay, anyway, right, so that's what we're left with. So we can recognize this left hand side. So in other words, this left hand side is actually pi of t, right? So we've just found a way to go from the definition of internal energy to the internal pressure is equal to T ds dV at constant temperature minus pressure. Okay, but now we have everything except this term is measurable quantities at the moment, because we have internal pressure is equal to temperature. That's cool, but we still have some stuff that is not measurable, because entropy, how the hell do we measure entropy? So we can go to our Maxwell equations, quickly go there, and we specifically look at the Maxwell relations, and then we should see somewhere, I just need to find it, there is a Maxwell relation that says ds dv at constant t is equal to dp, or is equivalent to dp dt at constant v, so which is what we want essentially, right? Because we have now a p, a t, and a v instead of a s, a v, and a t. Okay, so let's plug that in. So then we go to T dP dt V minus P. Okay. So that is what we wanted. So now we have an expression for the internal energy in terms of measurable quantities. Right. So how do we use that? So for a perfect gas, so let's say for a perfect gas, my word, struggling to write it down. For a perfect gas, we require what? What information do we require in this equation? Well, we need a function of P. Do you agree? Because we need something that says, something that says d something, so dp dt and minus P. Okay, to plug into this equation on top here. So for a perfect gas, we know that PV is equal to nRT. So in other words, if we want to make it a function of P, we will say P is equal to nRT over V. Right. So that means that pi of t, let's call it perfect, is equal to t times d dt. You can technically write just the formal derivatives here, but I'll keep it in the partial notation for now, over v minus, we said p, so everywhere where there's a p here in this equation on top here, you substitute p in, right? Because we have what p is, if that makes sense. So p is like your variable that you use. Okay, so there was a minus p here, and p is nRT over v. So that's all I'm doing. Okay, so that leaves us with t. What is the derivative of nRT over v 2t? So the only thing that can be derived or the derivative can be taken to is t. The derivative of t to t is just 1. So in other words, we're left with nRT over v. So minus nRT over v. And then you see these two things are the same thing. So that gives us 0. So that's a check. It's because at the beginning we were asked to prove that the internal pressure for an ideal gas is 0. Right. Okay. For a van der Waals gas, what is our equation of state? Well, the equation of state for a van der Waals gas is that P is equal to nRT over V minus NB minus A n squared over V squared. So, because A and B are just, so A and B are just constants, we can ignore them, but okay, let's plug these things into, maybe I should go to a new page. How do I lasso again on this? That's, aha. We go here. There we go. Okay. That is what P is. So, I lost the square. Okay, so P then needs to just be substituted into our equation for the internal pressure, right? So we have that it's T times dP dt at constant V minus P. So we just substitute this P now in everywhere where we see a P. So it's T times d dt of nRT over V minus NB minus A n squared over V squared. Right, and then we have here a minus P, which then gives us minus nRT over V minus NB minus A n squared over V squared. Okay, what is this derivative? So this is T times then, so the derivative is only applicable to this first term because this first term has a t in it. Second term has no t in it, so the derivative for the second term is 0. So this first term becomes just nr over v minus nb. Second term becomes 0, so that's just that, and it becomes minus nrt over v minus nb plus a n squared over v squared. And again, we can see that these two terms, let's highlight them in just a different color. This term and this term, it's the same thing. So we're subtracting them from one another, so we're just left with a n squared over v squared. Right. So basically what this tells us is that our van der Waals gas's internal energy is, or relies, or is dependent, that's the right word, is dependent on this factor A, or the A factor, which of course controls the attractive interactions, well, not controls, but is indicative of the attractive interactions in a van der Waals gas, and that gives us that for an isothermal expansion of a van der Waals gas, the internal energy would actually increase. contrary to what for a ideal gas, it won't really, there won't be any change. So just an interesting fact that you would get. If we had a negative value, then we would have that the internal energy would have decreased with the expansion or isothermal expansion. Yeah, so basically that's just what this tells us. There's an increase in the internal energy with an isothermal expansion. There's also a little part in the notes where I explain that a little bit further, which you can read up on. Alright, so I think this should have made sense. The only difficult part really is substituting in the equations of state for the pressure, because I know that sometimes it's confusing. You see a P here and then substituting in the P in at a later stage is a bit more difficult, but I think it is, I wrote it out quite nicely in two separate places, so it should be fine. Alright, if not, just rewatch the video. That's always a good way. That's why the videos are there, so that you can rewatch it 10 times, and then hopefully after the 10th time it makes sense. Okay.